This is Julius Bredt, a German organic chemist who proposed a rule in 1924 that shaped the way scientists understood organic chemistry, until now. The laws of chemistry are the invisible architects of our world, shaping everything from how our body works to the materials we use, and governing the fundamental rules that define the structure and behavior of matter. Julius Bredt's proposal is one of these rules. It explained why certain molecular structures were considered impossible to form. Precisely, it stated that double bonds structures where two carbon atoms share two electrons could not exist at the bridgehead of certain bicyclic molecules, which are molecules made of two interconnected rings like in these examples. You see three very similar molecules called Norbornene isomers, but according to the Bredt's rule, only the one on the left can exist. The reasoning behind this rule lies in the geometry of these molecules. For a double bond to be stable, the atoms involved must line up in a flat, planar arrangement. However, in a bicyclic molecule, placing a double bond at the bridgehead would twist the structure into a strained, unstable shape, like trying to force your back into a sharply bent position. According to Bredt's rule, the strain is so severe that these bonds simply couldn't form. This sounds all logical to chemists. This rule became a fundamental guideline in organic chemistry, shaping the way molecules were designed for everything from medicines to materials. Bredt's rule made its way into every chemistry textbook, standing as an immutable law. However, it also acted as a barrier, limiting chemists' ability to explore certain molecular shapes and create new compounds, especially in drug design where complex three-dimensional molecules are often needed for therapeutic effects. For decades, Bredt's rule stood largely unchallenged, with only scattered and inconclusive attempts to break it. These early efforts often failed due to harsh reaction conditions, low yields, or the rapid breakdown of the desired molecules. Scientists remained skeptical that such impossible structures could ever be synthesized in a useful way. That changed with a groundbreaking study by Neil Garg and his team at UCLA and published in Science. By rethinking the problem and leveraging modern chemical techniques, they developed a method to create anti-Bredt olefins, a new class of molecules with double bonds at the bridgehead that defy Bredt's rule. Garg's team combined theoretical models with a carefully designed experimental approach. They started with precursor molecules called silyl pseudohalides, specifically designed to overcome the challenges posed by Bredt's rule. By treating these precursors with a fluoride source, they triggered a chemical reaction that allowed the double bond to form at the bridgehead. To stabilize these highly reactive and short-lived molecules, the team used trapping agents, other chemicals that quickly react with the newly formed anti-Bredt olefins, transforming them into stable, usable compounds. This process not only proved that anti-Bredt olefins could exist, but also showed that they could serve as building blocks for more complex molecules. Why this matters? The ability to synthesize anti-Bredt olefins is a major breakthrough because it opens up new possibilities in organic chemistry, enabling the creation of highly specific intricate compounds, particularly important in drug development such as those used to treat cancer or neurological diseases. Unlike typical molecules, anti-Bredt olefins are chiral, meaning they can exist in two forms that are mirror images of each other. This property is critical in pharmaceuticals, as one form of a molecule might be highly effective as a drug, while the other could be inactive or even harmful. While drug discovery is one obvious application, the implications of this work extend to other fields as well. This research represents a significant shift in the way chemists can approach molecular design. Anti-Bredt molecules could be used to develop new materials with unique properties or serve as intermediates in industrial chemical processes. The study also highlights the potential of working with highly strained molecules, which could lead to innovations in areas like biology, catalysis, and materials science. This discovery is about more than just defying a century-old rule. It's a reminder that scientific rules are often guidelines based on what we know at the time. The authors of the new study argues that adhering too strictly to such rules can stifle innovation and creativity. It's a testament to the power of challenging assumptions and thinking outside the box. By challenging Bredt's rule, this team has not only rewritten the chemistry textbooks, but also opened the door to previously unimaginable possibilities in synthesis and design. As scientists continue to explore these once impossible molecules, we may see new breakthroughs. Please don't hesitate to comment, like, share, and subscribe if you find it interesting. Thank you for listening.